A recurrent network is really an ordinary feed-forward network with one prior wired into it. The same small computation runs at every step of the sequence, and a hidden state gets carried along, a running summary of everything seen so far. So the cell takes two things in, the current input and the state that arrived from the previous step. It mixes them, squashes the result, and hands the new state on to the next step. That is the entire architecture. Not a stack of distinct layers, but one layer applied again and again down the length of the sequence, feeding its own memory forward. Written out, the new state is the hyperbolic tangent of a weighted sum, the current input through one set of weights plus the previous state through a second set of weights plus a bias. The thing to notice is what is missing. Nothing in that rule depends on where you are in the sequence. The weights do not carry an index for the step. One cell, reused all the way down the stream.
So it is just a normal network that we run in a loop.
That is exactly it, and the loop is the whole point. Because the weights are shared across every step, this is the same move the convolution made, with time standing in for space. Weight sharing across positions gave us translation equivariance for images. Slide the picture over, the feature map slides with it. Weight sharing across steps gives time translation equivariance. For sequences, shift the input in time, and the output shifts the same way. The network cannot tell absolute position, it only sees relative structure. And just like the convolution, the backward pass turns that reuse into a sum. The gradient for the shared weights accumulates over every step, the same running total over a shared axis we saw for images. Reusing one cell is not a convenience. It hardwires an assumption about the world the sequence came from. The rule that turns the past into the present is the same rule at every step. The dynamics do not drift. Step 10 and step 10,000 are governed by identical weights. Call it the homogeneity bias. Time is assumed to be homogeneous. The machine that generated the beginning of the sequence is the machine that generated the end. And when that assumption fits, the payoff is large. One cell handles a sequence of any length at all, with a fixed, tiny number of parameters. Feed it 3 symbols or 3,000, it is the same weights doing the work. There is no separate machinery for step 1 and step 100, so every step of every sequence is training signal for that one shared cell. That is the sample efficiency win we have been tracking all series. The more you constrain the model to reuse structure, the less data it takes to pin that structure down. And in principle, the state is unbounded memory. There is a path through the hidden state from the distant past all the way to the present, no matter how far back it began.
If the state can carry everything forward, why would it ever forget?
That is the right question, and it is where the bill comes due. The architecture gives you that path from the past, in principle. Whether the learning can actually use it is a different matter entirely. To see why, we have to look at how the thing is trained, because the cost is hiding in the backward pass. Here is the one real difference from the convolution. The convolution applied its kernel to fixed input positions. Every window was there in the data from the start, sitting side by side. The recurrent cell feeds its own output back in as the next step state. The input to step 5 is partly the answer the cell gave at step 4. So the dependency is not laid out in space, it is strung out in sequence, and it can reach arbitrarily far back. That one change is what makes recurrence powerful, and it is also what makes it hard to train. To train it, you unroll the cell across the sequence, one copy per step, and backpropagate through the whole chain. It even has a name, backpropagation through time. And there is exactly one twist worth remembering. The gradient arriving at a step comes from 2 places, and you add them. Some of it flowed back from this step's own output. The rest flowed back from the future, through the next state, because this step's output became the next step's input.
And that plus sign is the whole trick.
That merge is the whole of backpropagation through time. You can read it straight off the code. The total gradient on the state is this step's output gradient plus the gradient handed back from the next step. Everything else is the chain rule you already had. How the gradients actually flow in full is its own from-scratch series coming later. For today, hold on to that sum, 2 arrows meeting at every step, one from the present, one from the future. Backpropagation through time is correct, and it is fragile. Every step you go backward, the gradient gets multiplied by a Jacobian, the local sensitivity of one state to the one before it. So the gradient that finally reaches an early step is a long product of these factors, one for every step in between. And that product is governed by 2 things, the spectrum of the recurrent weights and the slope of the hyperbolic tangent, which is at most 1 and usually less. Now watch what a long product of numbers below 1 does. It shrinks towards 0, exponentially in the length. The gradient to the early steps vanishes, and the model gets almost no signal about long-range structure. Push the other way with factors above 1, and the product explodes instead. One bad sequence can wreck the weights. This is the vanishing gradient problem, and it is worth seeing clearly for what it is. It is not a bug, it is the bill for the inductive bias. The architecture does give you a path from the distant past to the present through the state. The learning dynamics are what make that path almost impossible to use. The cell can in principle remember something from 100 steps ago. In practice, a plain recurrent network reaches maybe a few dozen. The reach it promised and the reach it delivers are not the same number. You can watch it happen. Train a character-level recurrent network on the opening of Alice in Wonderland, and the samples walk a recognizable arc. First random characters, then a plausible mix of letters, with vowels and consonants alternating and spaces about the right distance apart. Then word-like fragments, then short real words. Then text that is locally English, but drifts in meaning across any longer span, because the long-range memory is exactly what the vanishing gradient denies it. The arc is the lesson. Viewers of the Next Token Prediction series met this same model from the sequence side. Here we are reading its architecture as a bet and reading the bill. The standard repairs target the Jacobian directly. Gated cells, the long short-term memory. And its relatives add a path the gradient can travel without shrinking. Clipping tames the exploding side. The honest throughline is that this one product of Jacobians problem is what drove gated recurrence, and eventually attention, which throws out the sequential state entirely. So let us grade recurrence the way we grade every architecture in this series, on the same 3-line card. The bias, time is homogeneous. One shared rule at every step, that is the bet recurrence makes about the world. The win when that bet is right, any length few parameters. One tiny cell reads a sequence of 3 symbols or 3,000, and every step is training signal for the same shared weights. That is the sample efficiency payoff. And the bill when the bet strains, vanishing gradients forget the distant past. The path from long ago to now exists in the architecture, but the product of Jacobians starves it of signal, and the model quietly loses the far end of the sequence. Notice it is the very same weight sharing that earned the win. The one cell that let us handle any length is the one cell whose repeated Jacobian makes the gradient fade. The win and the bill are 2 readings of a single choice.
So is the bet worth making?
When the sequence really is generated by one unchanging rule, and the structure that matters is nearby, it is a very good bet, and it costs almost nothing to make. When the thing you need to remember sits 1,000 steps back, the same bet is why the model cannot hold it. That is the whole shape of an inductive bias. The assumption that buys you cheap learning is the very same assumption that bills you when the world does not comply. Recurrence bets that time never changes its rules, and pays for unbounded reach with a memory that fades.